My name is Shane MacBride, and I'm going to be showing you a short video of what my group decided to do for our final AI project. I worked with Mann, Forrest, and Jeff Guzman. The problem that we were trying to solve was the queens problem. So given an in-by-n grid with a randomized set of queen locations, one per column, configure the grid so that no queens can attack each other. We implemented the stochastic local search to solve this problem. The input was a randomly generated board of n queens. The output was one possible solution for the n queens with no attacking pairs remaining. To accomplish this project, we use a lot of different technologies. For example, we use LÖVE, a framework written in the LÖVE scripting language, GitHub to host our code and collaborate, GIMP to edit the graphics so that they appeared correctly, and also Slack to communicate throughout. In the LÖVE framework, there's an update function that's called every frame that's rendered to the screen. And after every iteration of this update function, it will check the H value for the global grid. And if the H value is 0, that means it has found a solution. If not, it continues running. And after a certain number of times, we chose 501. If there is no solution, we deem the board hopeless and regenerate a completely random new board to try again. The time to solve the algorithm compared to the n value of the board closely resembled our prediction of n squared. Since our algorithm implemented a lot of random functionality, it's no surprise that there is a large variance in the times taken to solve the problems. So for example, if you look at an n value of 64 by 64, you could see that the time taken to solve it was as low as 27 seconds, while also as high as over 120 seconds, which is 4 times that. This is a 16 by 16 board of queens that has been solved. On the top right of the screen, you can see the elapsed time, which is how long the algorithm has been running for, or has ran for. In this case, our algorithm for stochastic local search solved the queens problem in 2.4 seconds. At the top left, I can designate a next n value for the board to run, and this will visualize the variance in elapsed time due to the random nature of our algorithm. So this one only took 0.8 seconds as compared to the last value of 2.4 seconds. Although the 16 by 16 is relatively simple compared to a larger problem such as 100 by 100, there is still a large variance in the time. So for example, we just got values of 2.4 seconds and 0.8 seconds. I've seen values of over 15 seconds for this problem. I'll run it again just for demonstration. 1.7. So this one is pretty typically in the 1 to 2 second range, although it can get higher. We implemented a dynamic n value for our project as well. So for the next n value, I'm going to go ahead with 40. So this will generate a chessboard of 40 by 40 and solve that using our stochastic local search implementation. As you can see by the flashes of red, there is a heat map on our board. So for any H value for a specific node, if it's higher, it will be more saturated with a red color. So light pink colors might have an H value of 1, whereas a H value of 3 heirs representing 3 queens attacking that node will be completely saturated with red. It's harder to visualize on smaller boards of 16 by 16 because the nature of the queens problem solves the vast majority of the board really quickly, leading to a H value of greater than 0 for only a small portion of the nodes. To more easily visualize our heat map implementation, I'm going to generate a 100 by 100 board of queens for the algorithm to solve. As you can see here, the saturated red nodes have a higher H value for that current iteration of the algorithm. This project was a team effort, as is demonstrated by the variety of contributions that my group made.